welcome to Generation Principles. Okay, this is chapter 13 of the study design for 2020, and as usual I started by creating a help sheet for you that I have made a hard copy of here and will have scanned and uploaded to OneNote, Compass, resources as usual. Okay, so if you want a closer look at that, basically I have the help sheet here. Now you'll notice this scanned version has some handwriting in there. Now that won't appear in the Word document because I'll upload it in two versions for you. One of them is the PDF like this, which is something you can't actually change, but allows you to have a look at the whole thing the way I've created it. And the other one that I'm going to give you is the Word version of it. Now the Word version allows you to obviously highlight and copy and paste all of the text that I have included here. Now what you're going to find is that this help sheet with Generation Principles is a mashup of both chapters 13 and 14, okay? So you can see here, there is a reference to power loss in transformer, okay, why we use transformers, okay? All of that stuff is in the next chapter. But because I have been creating and collecting useful information over years of doing this, you can see that what I've done is I've put it all together in a sheet that is actually a lot closer to what you would use in an actual Saccharin exam. Now, in addition to this, you would add the DC electric motor information that I created earlier as well. Don't forget you get a double-sided A4 sheet of notes to do the SAC with, all right? Which means feel free to use all of that space. Obviously, you can minimize the amount of space that you use by manipulating all of this stuff and cutting bits that are obvious and you don't need anymore and things that you do remember, okay? Statements like Faraday's law, Lenz's law, all of these things that are important, you should keep, and also the shapes of the graphs. Often SAC questions will ask you to interpret the shape of one graph as compared to the other. So you'll see here that there's a graph of flux and a graph of voltage, and they are related to each other. Okay, so this graph gives you this graph, and also this graph gives you this graph, and so on. So it's important that you interpret the graphs appropriately because there's a lot of marks wrapped up there. Okay, so what I'm going to do here is this is going to be the lecture part of it. All right, I'll refer to the help sheet as we need to, but in reality, these are the notes. Okay, as usual, the notes are here already, and they will be also under Compass resources if you want to download and print them. All right, I suggest you do download and print them only because it's just having a paper version just seems so much more real, okay? Unless, of course, you're using OneNote and you're actually annotating and doing that way. Okay, in Generation Principles, what we're talking about in Generation Principles is the link between magnetism and electricity, okay? They were linked together a long time ago by some really clever scientists, and what was discovered was that you can use magnetism to create electricity. You can use electricity to create magnetism. All right, here I have an iron nail wrapped in copper wire. You may have done this before, not exactly sure, but you know, this will demonstrate how one of the links that we draw between electricity and magnetism. Okay, so this is a copper wire, a really good conductor, wrapped around an iron core, basically. We have some pins here, which are just very light, and they are also mostly iron with some carbon, so steel. All right, if I now run a current through the coil around the nail, you should see that the magnetic fields that are generated should now lift. Oh, come on, if the connection is good. Notice lifting the pin, okay? So the iron, the nail and the copper wire become magnetic with the active current running through. And if I remove the current, the nail should drop immediately, which it does, okay? So, as you can see, from the work that you've done previously, you know that current running through a solenoid generates a magnetic field by the sort of right-hand grip rule, okay? All right, so that's one demonstration linking magnetism to electricity, and the other one, which I think is really cool, is... All right, what I have here is a coil wrapped around a clear tube, and that way I use a clear tube because I wanted to be able to see the movement of the magnet as it moves through the coil, okay? Now, all of our generation principles are based around this principle here of a moving magnetic field cutting the wire, the coils of the wire, and inducing a current. So in that first example that I showed you with the nail and the copper wire wrapped around it, I introduce a current. That current creates a magnetic field, okay? This demonstration is kind of the opposite. Here, there is no current, but what I'm doing is introducing a magnetic field from a permanent magnet, so the magnetism is already there. I am connecting it, completing the loop here, through what is a microammeter that you can see right here. And what I'm basically going to do is I'm going to put this sponge there to protect the magnets, because we don't like to bang magnets, because it's not good for them. And what we're going to do is I'm going to drop these magnets. There's 3 of them together, really, really strong magnets, courtesy of Mr. Coventry, who loaned them to me. I'm going to drop them through this tube, and you're going to see me basically inducing current. Now, I'm going to zoom in so you can see the needle. You can see the needle, and hopefully get this stuff out of the way. Now, hopefully this will be pretty clear and easy. Watch as I do. 3, 2, 1. Now, notice the needle moved. Now, if my editing skills are good enough and I can figure it out, I will do, in the video, I should be slowing that down so you can see the needle move, all right? Now, if I can manage to do that and you see the needle move, I'll do it again. So I'm going to drop the magnet again, 3, 2, 1. The magnet go past there in the clear tube, and as it passes by the coils, a current is induced, which you see here in the movement of the needle backward and forward. Okay? So that's what we're going to be studying today, the idea of how current can be generated from magnetic fields and how magnetic fields can be generated from currents. Okay? And these are generation principles. Okay? So, chapter 13. Let's go through the initial stages of these notes, and you can see here we're basically going to introduce a new variable, a new thing that that you will need to keep in mind when you're dealing with this, and that's the idea of flux. So, as you can see here, we use this symbol here, which I think is 5. You draw it like this, nice little circle. It's kind of like a little bit like theta, but you know, sort of the other way around a bit, and with a nice long tail. So this is the symbol we give to flux. All right, and its unit, the unit of flux, is the Weber. Okay, so basically W, big W, little b. All right, that is the Weber. Okay, now what is flux? If you look at the formula for flux, it is equal to the magnetic field strength that is threading a particular area, cross-sectional area. So, what that means is, if I have a wire loop and it has a certain radius, for example, to work out the magnitude of the flux threading this loop, I imagine maybe there's a magnetic field coming out of the page, okay, as this loop in this example is being immersed in a field, a magnetic field B, that is coming straight at you from the board. The density of lines inside the area of this loop is the definition of flux. Okay? So the flux outside the loop does not count. Alright? The loop can be round, it can be rectangular, it doesn't matter, or a nice perfect square, it doesn't matter. But when you're calculating flux, you want to know what is the strength of the magnetic field and what cross-sectional area is it threading? And it's the product, multiplication of those two values, okay? And I've put this in here because that is the symbol for perpendicular, okay? So, what that means is, show you this model. Back to this guy, all right? Remember our little DC motor, okay? Well, you have your loop, orientated vertically, for example, okay? Now, orientated vertically, I've got my two magnets here, north pole facing this way and a south pole facing that way, so I've got a nice field threading through here. There's a nice magnetic field, a B, threading my loop, okay? The perpendicular symbol tells us that the maximum amount of flux threading this loop is when the loop is in that orientation, which means that the cross-sectional area is perpendicular to the field that is threading it. See that? The field's threading it like that. Now, if I were to turn this loop to the side, you can see that now, if you were to look at the cross-sectional area of what is actually facing that field, you can see there is now less flux actually threading that space, okay? Because now there are flux lines that were going through this loop in this orientation, that as this loop now rotates, now those flux lines that were below and above the loop are no longer going through the loop, so the flux is actually reducing, okay? So that's all that means. Now, obviously, if you go from now to now, you go from maximum flux to zero flux, okay? Now, in that motion, what you end up doing is generating a pulse of EMF, okay? That's basically how we determine how much voltage we can generate out of that, okay? Out of that motion. Now, again, flux is moving from north to south through here, maximum flux, okay, in its current orientation. You can juice it all up. There's lots of magnetic field lines, but let's say we're not moving, okay? It's just sitting there stationary. And I connect my voltmeter to these wires and I read the voltage, and the voltage says 0. What's wrong? Why is it 0? I've got lots of flux threading through this wire, through this loop. That's the definition, right? That's how we make electricity. Well, kind of. Basically, how do you make electricity? It's by the changing of flux. In this orientation, yes, you have maximum flux threading, in other words, maximum magnetic field lines, threading that loop, okay? Yes, there's a maximum. But if they stay constant, then the voltage that you read off these cables will be 0, okay? So whether it's on or off makes no difference. You're not getting anything, okay? When do you get something? When you move. In that moment, in that time that you go from vertical to perpendicular to the field to parallel to the field, so maximum flux to minimum flux, in that you get a pulse, okay? You get a pulse of EMF, all right? So, in this orientation, the field is threading the loop through this side of the loop. As it turns its quarter turn, it goes from maximum flux to minimum flux, all right? So threading the loop through the front. Then, in the next quarter turn, it's going from zero flux to maximum flux, but threading the loop now through the back side of the loop. Because yeah, believe it or not, there's a front side and a back side. Makes a diff, all right? Trust me, I know what I'm talking about. So, as the flux is threading, say, the front of the loop, I've just decided that's the front of the loop. As I move from here to here, it goes from full flux through the front of the loop to zero flux. Then it goes from zero flux to full flux through the back of the loop, all right? And then, as I continue my turn, it goes from full flux through the back of the loop to zero flux through it, and then all the way back to zero to full flux through the front of the loop. Now, I don't know, for those of you that are really like thinking about what you remember about AC voltage or AC current, but you might be thinking that, oh, is this where the whole sinusoidal wave of AC comes from? And good, yes, basically. If that's what you were thinking, awesome, because that is what AC is, okay? So as flux, magnetic field lines reduce in the loop through the front of the loop to zero, then they go from zero, but now through the back of the loop. You're getting these pulses of voltage to go up and down and up and down and up. And hence why you end up with current changing direction every half turn, okay? So in one turn, you're going, yeah, you know what I mean. All right, so that is the idea of changing flux, okay? Now, obviously, that leads us to another formula. So you can see here, this is the formula for flux. Flux is equal to, and sometimes you'll see flux there with a little b on it just to remind you that this is magnetic flux, because there's obviously other kinds of flux, is equal to the magnetic field strength. So this is in Tesla. Threading, well, the perpendicular area of some loop of wire, okay? Now, let's say I have a coil of wire that looks like this. And let's say it has a cross-sectional area of 0.1 meters squared. And let's say I have a magnetic field of 1 Tesla. Now I ask the question, well, how many, or what is the flux? What flux do I calculate out of this calculation? Really simple, you know, BA, and I'm saying it's all nice and perpendicular. So I'm going to go, well, the flux through the coil here is BA, which is equal to 0.1 times 1, which is 0.1 Weber. Reasonable? I hope so. Now, what change would I expect in that calculation? What change would I expect in that calculation if this wire actually wasn't just one loop? Maybe I want to make lots of electricity. You know, I've got to run something that needs lots of electricity, all right? So let's say I want to run something with lots of electricity. So this coil isn't just one coil, it's maybe a few coils. And then out it goes, okay? So now it's got 2 coils, all right? How does that change the magnitude of the flux moving through that coil? Look at the formula. Ask yourself, is there anything built into this formula for flux that tells us about the number of loops? Nope, there isn't. Okay. That means the number of loops does not change how much flux you're actually calculating, okay? that makes no difference to the value for flux. The internal area, the cross-sectional area is still 0.1 meters, the field is still 1 Tesla, the amount of flux threading that loop is still 0.1 Weber. That's it. But surely you must be thinking that having more loops cutting field lines would make some difference. Yeah, you're right, it does. But not to the magnitude of the flux. It does make a difference to the magnitude of the voltage that you are actually generating. So there are a couple of things that change how much voltage you can get out of this system. All right? And how do we calculate voltage? Well, it should be here somewhere. We calculate it using Faraday's law. Faraday's law, Faraday, you should look him up. He was a brilliant scientist from from quite, I think, the 1800s. One of the guys, I think, that demonstrated the new electricity, the new science of electricity to Queen Victoria. Like that kind of time. That's who this person was. But really renowned for being a really good teacher, actually. Anyway, so Faraday came up with this nifty little calculation. Basically, EMF, yes, you have to learn how to do that E, just because it's really cool, okay? E, so that is your EMF, okay, is equal to the negative, now that bit isn't really Faraday, N, and they've got a capital N there, don't know why, it's ugly, change in flux over change in time. So this is how you calculate voltage based on change in flux. Obviously, as I was showing you just now with the electric motor, if the loop is stationary, sitting there, not moving, I just said that there is no voltage. You get no voltage. Do you have flux? Well, hell yeah, there's a magnet, there's flux, okay? It's only in the act of moving, and the only time you have a voltage is while it's moving. If you just do this, bam, you'll get a pulse of EMF, and then where you stop there, it'll be gone. It's the constant moving that gives you a changing flux, which then induces a changing electric current, okay? So it's in that movement, and that movement is implied by the fact that it's the changing flux and how quickly you're changing it. That's delta time. So how quickly are you actually spinning? So when you look at this formula here, what we're seeing is the EMF is related to, or dependent on, how many coils. Okay, so that's where your EMF is affected when you add coils. Okay, that's what you change, not the magnitude of the flux. Okay, this here is the magnitude of the flux that you're actually changing. And this is how quickly you're doing it, all right? The time of change. In other words, spin it faster. If you spin it faster, it means it takes less time for the coil to move around. So the period with which, or the speed with which you're rotating it. So how long does it take for the loop to get all the way around? If you spin it faster, it takes less time, okay? So when that value gets small, obviously that value gets big, all right? If you increase, now you know that this here is actually equal to the magnetic field density and the cross-sectional area. So how do you increase EMF? Can you see that? Did I write off the board? I think I did write off the board. Okay, sorry. This is what I just wrote there. Flux, changing flux is equal to BA. All right, so how do I increase the EMF output? Well, I have to increase the flux as well. If that value gets bigger, this value gets bigger, okay? Which means I can do two things, one of two things or both. I could make the field stronger, 1 Tesla becomes 2 Teslas and 3, Or I can make the cross-sectional area bigger, so there's just more flux threading that space, okay? Now, all of those things will make the EMF bigger, okay? So that's really important to understand that because a lot of questions are based on that, okay? So, moving on, is there anything there that is particularly important? Okay, all right. Now there's lots of different ways that we use this concept, okay, in electricity, the way we make electricity, okay? So there's another model that I'm going to show you. All right, so what we have here is a little model of a generator, okay? So we're using the interplay between coils of copper wire, okay, wrapped around a metal core, suspended. So these are the coils, and they're on an axle that allowed it to spin. These are two magnets. So there's a permanent magnetic field moving in one direction through this coil. And you can see the coils have, in this orientation, full flux moving through these coils. In this orientation, zero, because the face of the coils is what do you call it, parallel to the field, and hence you should have nothing there. Now, there are two little LEDs connected. Only one of them ever works, okay? LEDs, as you know, allow current to move through the circuit in one direction and not the other, okay? So if I spin this in one particular direction, it will create a pulse of current that will light up one of the LEDs, and if you spin it in the other direction, it lights up the other. Like I said, pretty much the green one is the only one that ever really works, okay? So, for the purposes of this experiment, and the reason it does that, the reason it's sending it through one direction and the other is because you'll see here, there's actually a clever little commutator. Oh wait, is this a commutator? Yeah. There's a commutator built in here. It's just a very simple version of a commutator which you would know about now because you would have done DC electric motors already. So this commutator only allows the current to move in one direction, okay? So if I spin this wheel in this way, the current is forced to go only in one loop, okay? And whereas without a commutator, if those were slip rings, then I'd just be getting a pulse left, right, left, right, left, right the whole time, okay? All right, so this is a model of a DC electric motor, but when I take a DC electric motor and spin it manually, okay, then it becomes a generator. It's pretty much the same exact configuration. All right, so I am going to, as you can see, if I spin it in this direction, you could probably see the light flashing, but I'm going to switch the lights off because it's way cooler with the lights off, and you can see that when I spin this loop, this what is essentially a DC electric motor but without a current running through it, I take the place of the current and actually crank it, and as you can see, if I do that, I'm producing a current, quite a strong one. Let's see, will the red work? Why doesn't the red work? That's really cool if the red one worked. Maybe we need to go faster. No, I don't know. It may have blown out. Who knows? But the reality is there. You can see that I am creating, you know, electric current by spinning a copper loop inside a magnetic field. How awesome is that? All right. And if they ever let us come back to school, I'll let you play with that when you get back to class. All right? All right, so you see these simplified diagrams of a generator all of the time. Here you have a copper loop, and suspended by magic, a bar magnet. That bar magnet, you've got a little arrow showing that the magnet is spinning. If the magnet spins, you should see the light globe light up. All right? That is the whole idea of generating electricity and how we do it. Okay? EMF. EMF has lots of names. Okay? So EMF, you should have this on your help sheet. Didn't put it on yours, but in reality, the EMF is voltage. It's called EMF, the electromotive force, okay? You can do curly E, that's EMF. And I think there's a couple of others as well. All right, there's it goes by a lot of names, all right? So it's really important that you know when you're asked about a particular thing in a question, that if they use one of the many names for voltage, that you know what they're talking about, okay? That you're not trying to calculate current or some other thing, all right? So, this is Faraday's law, okay? As we just mentioned. Faraday's law has the number of coils, the change in flux, and how quickly you're changing it. And then there's this negative sitting right there. What's this all about? What is that negative about? Well, that negative, if you look at your help sheet, on your help sheet, I have been careful to include Faraday's law and Lenz's law, okay? So Faraday's law, the EMF is equal to, and that's the formula. So this describes the fact that a changing flux will induce an EMF, some voltage, okay? Now, what does Lenz's law tell us? Lenz's law simply describes the direction of the induced EMF. Now, an induced EMF, so this is when you spin these magnets, you are inducing an EMF, you're making electricity, okay? So, there are rules that govern how you change your flux, governs the direction in which the induced EMF will actually flow, okay? And that's based in Lenz's law, all right? And a really wonderful example of what that means is that if I try to push a conductor through a magnetic field, as that conductor cuts the magnetic field line, so obviously magnetic field lines say, for example, vertical, and my conductor is cutting through those lines, okay? That is really important. Your conductor needs to be cutting the lines to actually induce any kind of current. Now, if I manually using, my breakfast chemical energy to push through the magnetic field, a current will be induced in here. Now, you know that if I have a current in a wire, that current creates a magnetic field. I showed you that right at the start, okay? So now, what do I have? Well, I have a conductor moving through a magnetic field, creating a current through that conductor, which then creates its own magnetic field. Understand? If that happens, or when that happens, that field from the induced EMF, as it's cutting through here, will start pushing on the field that's here, because magnetic fields act on each other, okay? That's a really important idea to get in your head. One field creates a current that then creates another field that pushes on the original field, okay? It sounds a bit confusing, but it actually does make sense. I've got a really cool demo to show you how that actually works. Now, what Lenz's law tells us is that the field that you create, that is created in response to the first field being present. So, in other words, the magnetic field that is being created in the conductor in response to the fact that that conductor is cutting another external field, those two fields will always oppose each other. They'll push on each other, okay? Now that makes a lot of sense by the rules of the universe, all right? See, if that wasn't the case, and the fields helped each other, then what would happen is one field would induce another field. Those two fields would push on each other in the way that accelerated them, and then the faster that conductor accelerated through the field, because these two magnetic fields, the one that was already there plus the one that's being induced, are helping each other. Okay, this is why Lenz's law does make a lot of sense. If the fields were in the same direction and they were helping each other along, all you'd have to do is start the conductor off, and then you'd have kind of free energy. It would just keep shooting across and getting faster and faster and faster, and that's it. You don't need fossil fuels anymore or anything. It's just a bunch of magnets, and you get free energy. Okay, so obviously that's not how the universe works. All right, there's always got to be some sort of a balance to it, and in the rules are that you don't just get free energy. You don't just get motion out of nothing, okay? Which means when you push a conductor through a field, that conductor will have a current running through it while it's being moved through the field. That current will induce a magnetic field, and that magnetic field will push back. So if I push this way, I should feel a push back. If I push this way, I should feel an equal push back while I'm doing it, okay? And just to prove that, all right, here is a demonstration I prepared earlier. Aluminium tube. Has to be aluminium or copper, can't be iron, okay? This demonstrates Lenz's law beautifully, all right? So, what I'm going to do is I am going to first demonstrate how quickly gravity pushes an object through this tube, okay? So, aluminium tube, a glass marble, no interactions between the two materials, okay? If I drop the marble through the tube, from the sound, even if you didn't see it, you could hear it just got through really, really quickly. Okay? One more time. Drop, comes straight out. Okay? This is a magnet I got off eBay. Another one of these really strong magnets. Okay? It's actually much smaller than the opening. You can see that this magnet quite easily fits and sits nicely in there. There's no resistance to its motion. It's just I'm gonna drop it, it's just gonna fall through. Maybe just like the marble. Who knows, right? Okay, notice because this is a magnet though, and this is aluminium, it's non-ferrous, which means it won't act on it, therefore it's not magnetic. It's not actually gonna stick to the tube in any way. Look, you know, it'll just fall off. All right, into my hand, okay? Just to prove this is a magnet, here's a manky old paper clip. Oh, look at that. Okay, so this is a magnet, definitely, okay? All right, now, watch. As I drop the magnet through the tube, I'm gonna let it go, and Lenz's law and Faraday's law together will take effect. That took a huge amount of time, okay, compared to the marble, the magnet. All right. Now, you know the magnet's way smaller than the tube, so obviously it's not gripping on the tube in any way, it's just falling, but for some reason it's falling really slowly. What is that reason? Well, glad you asked. The magnet moves through the tube, okay? The tube is metal. It's a conductor. So a magnetic field cuts through a conductor. The conductor then becomes electrified. So there is a small current running through it as the magnet moves. Notice the magnet must keep moving, okay? Now, the faster the magnet moves, the higher, or the greater the magnitude of the electric current that is being generated. So if it's moving quickly, you know, changing flux, the time is very small, you're getting a lot of current. The more current you get, the more magnetic field is induced. But in which direction is that magnetic field being induced? Well, it's going to be induced in a direction such that opposes the motion of the magnet. So I would have dropped the magnet either through a north, with its north end down, or its south end down, okay? If I dropped it with its north end down, then a current will be generated in here, in this tube. That tube will then that current will then induce a magnetic field. But which way will the magnetic field be pointing? It'll point in a way to try and stop the magnet from falling. So if the magnet is falling with its north end down, this becomes magnetic with its north end up, all right? Now, if it's not moving very fast when you drop it initially, it's going to be creating a very weak magnetic field, allowing the magnet under gravity, because it's got some mass there, to actually accelerate. As it accelerates, it induces a higher amount of current, okay, a larger amount of current. The more current, it then creates a stronger magnetic field that's associated. That magnetic field gets really strong. When it gets really strong, it slows the magnet down, okay? As it slows the magnet down, it starts to drop the amount of current that it's actually generating. So the opposing magnetic field becomes weak and it starts to speed up again. So it's doing that all the way down and taking its sweet time to get out, okay? So that is the idea of Lenz's law, okay? Now Lenz's law tells us that the direction will oppose. The direction of the induced current, or the voltage, will be opposite to the change in flux that generates it. Now that makes this part of this graph make a bit more sense. Now the only other really big thing that you need to understand here is the relationship between the change in flux, this is a change in flux graph, and the change in voltage, okay? So this is something that you really have to spend some time to get your head around. If you don't, it just makes a lot of this stuff a lot harder to understand when you're trying to do things, okay? All right, so how do we understand this graph? This is the best way that I can think of to explain it, but relationship between flux and the generated EMF. In this position, you can see that we have maximum flux, and we'll say through the front of the loop here. That's this. So as this rotates from here to here, okay, we go from maximum flux to minimum, okay? So at that moment, as this wire finally, you can see that the area exposed to the magnetic field changes initially kind of slowly, because its maximum is a little bit less, a little bit less, a little bit less, and then as you get to this bit here, you go from something to nothing, okay? That kind of represents a really, that's the moment in the turn of the greatest generation of the EMF is right at that moment there, when you go from almost nothing to nothing, okay? So that corresponds to, there's your maximum flux, the loop starts to turn its quarter turn, okay, so the EMF is being generated. At that moment just there, where it goes from some loop facing the magnetic field to nothing, that gives us a peak here of EMF. Okay, so in the first quarter of the turn, you go full flux, it gives you maximum EMF. Now there's a couple of things to keep in mind when you're looking at this graph, all right? One is, you can see that the gradient of this graph is negative. And by Lenz's law, the pulse of EMF is positive. Okay? It remains negative all the way down to here. If you look at your tangents, it is negative, negative, less negative to almost flat. That whole region corresponds to, from here to here, corresponds to positive pulse of EMF. Okay? Now, in this first bit here, you're threading the front of the loop, all right? Then you're threading the back of the loop as you're moving around, okay? So it is maximum flux to minimum, then it's minimum to maximum. So these are, you look at these graphs in terms of quarter turns, okay? First quarter, second quarter. Now, you'll notice that if we look at this loop, it goes from threading through the front of the loop, bam, okay, to 0, then going through the back of the loop, bam, to full, okay, to full, all right, and then it continues its turn around 360 degrees to emptying again, and then back to its original position for the last quarter of the turn. So what you're looking at here is a negative gradient corresponds to the positive pulse in the EMF. The positive gradient which is positive through there, a maximum through here, positive through here, okay, corresponds to the negative pulse in the EMF. And that flipping of going one's positive, the other one must be negative, that's Lenz's law, okay? It's giving you the direction which makes this make sense, all right? Okay, now the only other thing that I need to get you guys to really understand here is that the gradient here, the gradient of this graph, okay, is the y value of this graph, okay? So, this is something that you learn and people go, yeah, okay, I get it. And then they go off and do questions and then completely forget how that works, all right? And that's the biggest problem you have with this section, with this little bit here. Let's say that the rise over run of this section of the graph is, let's say it's 3 and that's 1, okay? So you've got a rise of 3, for example, over a run of 1, okay? So 3 over 1, that'll just be 3 over 1, which is 3. So the gradient there, or m, in your y equals mx plus c graphs, your m is 3, okay? Oh, it's actually negative, isn't it? Because that's a negative there, right? That is a negative gradient, all right? Then, what does that gradient at that spot correspond to here in this graph? Well, it is, you've got to flip it, okay? Lenz's law. You can't, if it's negative there, it's got to be positive here. So you go up 1, 2, 3, it's that spot there, or whatever corresponds to that spot there. So if you went across to where these two line up, the gradient 3 there is the value 3 off the y-axis there. That's how they relate to each other, okay? Well, the negative of the gradient because of Lenz's law, okay? So here, what is the gradient here, for example? So if you remember any of your algebra from your graphing stuff that you've been doing for a little while now, the gradient of a flat horizontal line is 0. What does that correspond to on the EMF graph? Man, 0. Every time this graph goes flat, you get a 0. All right? Why? Because you are reading the value of the gradient, which is a description of how the line is moving, as a single value of the EMF graph. Okay? That's the rise over run. All right. Does that make sense? Yeah. I mean, look at it. Look at the, can you see the formula that I wrote just over there? Okay. Change in flux. So the change in flux here is, now you can't see what So here you can see the change in flux is how high up, that's your rise, and how quickly you do it, that's the, well in this case it's based on angles, but yeah, it's usually the time. All right. Oh, I might cut that bit since the graph doesn't want to work with me. All right, what I'm going to do now is, rather than devote a separate video to the questions and the examples, I find that in this area, it's actually a lot easier to demonstrate what's going on by actually doing some of the questions, because it's really hard to explain how the right-hand grip rule is very useful. Is very, very useful in solving these questions. So, for example, what I mean is, let's say, now I said earlier that if I move a current, if I move a conductor through a magnetic field, it will induce a current, okay? Now that current there, if I'm moving it, now this is a completely separate thing to how a DC motor works. See, with a motor, you connect these to a power supply, okay? You put the electricity in, okay? The electricity goes in and it induces a magnetic field that magnetic field pushes on the field that's already there and it spins, okay? Like your vacuum cleaner, your blender, your washing machine, all right? That's how that works. But now if we look at this model and say, no, this is now a generator. I'm gonna use it to make electricity, which means now I gotta go and boil some water and turn a turbine and make it spin, all right? So if I make it spin, all right, its function is now completely different to what an electric motor is. Its function now is simply, the more you spin, the more electricity I get out of you. That's what this is for, okay? Which means if I now push this loop through that magnetic field, right? If I push it through here, it will induce the current, which is what I want, okay? But as it induces that current, as I've just explained, it will create its own little magnetic field, okay? Sort of right-hand grip rule as I push it down, okay? So it's going to create its own magnetic field. But what does that actually mean to the loop? Well, that magnetic field has to oppose. It has to oppose what I'm trying to do, okay? So if I'm pushing it down through the loop, by turning it, okay, with my turbine or whatever that I'm using, okay? If I push it down, okay, and I know that there's a north-south, so there's a field, this conductor, this edge of the conductor is being pushed down through a field that is moving like this, okay? That's the direction of the field, north-south. If I push it down, it will it'll generate a current, that current will generate a magnetic field, and that magnetic field has to resist what I'm doing, which means it's going to experience a retarding force up, all right? Now, for that to happen, which way is the current going through this arm while I do this? Well, I use my right-hand rule. Not my right-hand grip rule, not my north finding rule, just my right-hand rule. Why? Because this is a field on a field. That's what the right-hand rule is for, okay? So, what that would mean is, if I'm pushing it down and the field is going in this direction, then it must experience an opposing force trying to stop me from pushing it down, that arm there, okay? Which means to do that, if I'm pushing it down, it's going to try and push up to resist that. Which means if my field is going north to south like this, which it is, north to south, then my palm has to go up to be opposite to the act that is creating it, okay? So, in that respect, my thumb is pointing back this way. I know the current has to be running this way through the loop, okay? As it moves from here to here, okay? All right, so that is the idea of, it's the same idea as the magnet falling through the metal tube. It creates forces that oppose the changes that are being made, all right? Okay, so let's do a couple of questions and see how you go with that, if this kind of makes it easier to understand, hopefully. Okay, first question, example 1. Multiple choice, flux, change in flux concept. Magnetic flux is a measure of what? It says, I've got here the intensity of a magnetic field passing through any given area of space, which is true. So you'd say this is the space that I've got a magnetic field through. Well, the flux through that space is the product of the magnetic field strength and the cross-sectional area of that space. So that is true. All of these others, the angle of the magnetic field to the area, no, it's not about the angle. The area of space through which field lines pass, that sounds reasonable. The area of space. No, it's not about area. It's about the amalgamation of area and magnetic density. How the magnetic field fluctuates in any... No, the fluctuation of the magnetic field is where your electricity comes from, and it's not specifically magnetic flux. So that's why it's D. If we move up to the next example here, example 2, just a basic application of the flux formula. Flux is equal to BA, so they've given you a wire with a diameter of 5 centimeters, which means it has, just don't forget, which someone always does, and it's incredibly frustrating when you see centimeters. We don't use centimeters ever, okay? Ever, right? So 5 centimeters is really 0.05 meters, and then a radius is 0.025 meters. So that's why these values come in here, and that is the area of the circle. And you multiply it by the strength of the magnetic field there, and that gives us 5.9 by 10 to the minus 6 Weber is the flux there. That's an easy question, just a direct application of a formula on the help sheet. Everyone should get that right. Okay, now, in this next one, the figure below shows a single loop of wire placed completely within a region of uniform magnetic field. Full flux, magnetic field lines going into the page, that's why they're X's, and you can see which way we're going to turn this loop. All right? Okay. And they've given us a magnetic field strength from Tesla there. The loop of wire has an area of 10 square centimeters. Now, again, 10 square centimeters, all right? How do you convert square centimeters to square meters? Well, 1 square meter is 1 meter by 1 meter, okay? The exact same square in centimeters is 100 centimeters by 100 centimeters. So, that gives me 1 square meter, whereas this gives me 10,000 square centimeters. So to convert 10 square centimeters to meters, you don't divide by 100, you divide by 10,000, okay? That is basically how you do it, and that works for everything, okay? Even if you're doing volumes, okay? All right, so now in this question, you didn't really need to do that because they didn't actually ask for that, it was just talking about the graph, but I know that that does come up sometimes, and you might, if you're not fully aware of how conversions work in area, now you are. All right, so 10 square centimeters. The question asks, which diagram below best represents the magnetic flux through the coil as a function of time if the figure above shows the situation at time equals 0? So at time equals 0, you've got full flux, all right? Now, this is, again, straight off the help sheet, straight out of the notes. The first quarter turn is from full to nothing, okay? This and this represent 1 full cycle of a loop in a magnetic field, okay? 1 full cycle. This is 2 full cycles, and so is this, all right? This is 1 full cycle. So, which diagram best represents the magnetic flux as a function of time if the figure above shows the situation at time equals 0? So time equals 0 is this, that's full flux, to 0 flux, to flux, full flux, threading the loop through the other side, then back to 0, then back to the original, okay? That's it. Again, I have, if you need to go back to that question, tons of notes on it just to make sure you start to wrap your head around what I'm talking about. Okay, what's next? My favorites. Here we go. Okay, Sophia and Max now move the coil. Okay, so this is obviously a different situation there. And in these notes, they always cannibalize big questions by chopping little bits out, okay? So Sophia and Max are moving a coil. You can see, now you've got to get used to these diagrams. This coil is moving in between the poles. And this is 3 different situations or 3 different times of the same situation. So you can see that here, the loop starts completely outside of the field. Now, because this is only high school physics, all right, and there's so much more to know, what we do is we say, okay, there's field lines between the poles. Now, you know very well field lines arc and curve and move all over the place, all right? But to try and make these kinds of questions doable, where you're learning the concepts, what we do is we pretend that the magnetic field lines exist only in between the poles, okay? Outside, 0. Inside, 4, okay? Obviously not true, but makes the questions doable at this level, okay? The field lines are moving north to south. So these are little things that even when I'm marking your sacks, all right, that last sack, that a lot of students don't do the basics, okay? Which is, this is a battery. Put a plus on it, okay? If it's attached to a wire, stick an arrow on it. These are basic things. This is how you get marks, all right? By actually doing what I tell you to do, all right? So it's really important that when I say, okay, there's a field, okay, identify the direction of the field, okay? Don't sit there staring at it blankly and go, oh, I don't understand anything, when you didn't do the very first thing that I said to do, which is put the damn field lines in, put some arrows in. The rest of the question comes to you when you do these little things. Okay? So if you're still in that boat of staring at a question going, I don't get it, how about trying some of the, advice, okay? Put some notation down, all right? It helps, trust me, okay? So you've got this field and it is moving up from north to south. This loop starts completely outside. The magnetic flux through the coil as it moves from position A through position B to position C is shown below. So you can see that now. Out here, moving from here, from this leading edge of the loop, okay, that leading edge of the loop, as it approaches and hits the field, it's going to be nothing, there's no flux. Then it hits the field and it starts to increase. Now, because it's a square loop, if you look at it and it's moving at constant velocity, the amount of area that is exposed is actually linear, okay? It goes up in a linear fashion, which is why you will sometimes see graphs that have a curve nature, and that's because you're looking at loops, you're looking at things that are spinning and twisting, okay? Or approaching from infinity and then going off to infinity. These give you curves that give you graphs that are curvy, okay? All right, whereas if we're saying that the field only exists in between the poles, when that leading edge hits the field, it starts to increase flux in a linear fashion, which then corresponds to a straight line in the graph, okay? It enters the field completely, but you can see that they've gone and they've been careful to show that the loop is pretty much the same size as the field, okay? So once it's in the field, it starts to leave the field again, all right? That's why it hits a maximum here and then immediately starts to leave and then immediately starts to drop. So now the flux is reducing, okay? Until the back edge, leaves the field. Okay? Now, that back edge is in green, all right? And I have found doing these questions a lot easier if you focus on a particular arm and a particular length and ask yourself, what's going on there? That then implies what's happening in the rest, okay? So, when that green line leaves, you hit the bottom again, all right? So that's where the graph then goes back to 0 change in flux. So the graph then goes back to nothing, all right? Now there's heaps of notes written there because, again, this is early on in the chapter, and I want you to make sure that you understand it. Now look, example 4 says, circle the letter A to D of the graph below that best shows the EMF induced in the coil as a function of time. And it's this graph, clearly, since I circled it already. Why is it this graph? Okay, well, ask yourself the relationship between this graph and this graph. All right? What did we say just now, like maybe 20 minutes ago? If the flux, it's the gradient of the flux graph is the y value, or the vertical value, magnitude of the EMF, which means if this is a constant gradient, and that's what a straight line is, a constant gradient, wherever you measure the gradient on a straight line, it's always the same. Doesn't matter where you draw your triangle, okay? So if you want to do your rise over run here, or here, or here, it's always going to be the same value, okay? It's positive. Lenz's law tells us negative, and because it's constantly the same value, it'll be constantly the same value while it enters the field. Once it's inside the field, it starts to leave the field again. Now it starts to leave it. Now, again, this gives us the same, because it's moving a constant velocity, it's giving us the same gradient, but the other way. So that's now the negative version of the gradient. That then corresponds to a positive pulse. So the gradient of that line is that value there, all right? And it's constant while it leaves the field. And as soon as it leaves the field, bam, drops to zero. These lines here are not real lines, okay? They're just there to show you, to have it lined up. In reality, I want you to try and imagine anywhere you see these vertical lines, okay, they don't really exist. Why? What's the gradient of a vertical line? That's right, undefined. Undefined means that that's not really part of the graph, okay? So I want you to try and imagine any vertical lines in these situations as being dotted, because they're not really there, okay? The only part of the graph that's really there is this bit here and this bit there, okay? That is the only part of the graph that actually exists, all right? So you're getting a pulse as it enters, and then an opposite pulse as it leaves. Those lines don't even need to be there, all right? Because sometimes I find people find that confusing, as in, okay, is that actually part of the graph? No, it's not. Okay, next. All right. Now, there's a couple of different ways that they can ask you questions about changing flux. You can move a loop through a couple of poles, as we just demonstrated. You can spin a loop inside, inside a magnetic field, like I've done over and over again with this guy. All right. The other way is you can also, let's say you were using magnets that weren't permanent magnets. Let's say you were using solenoids. Okay, in other words, coils to make magnets, right? If you're using coils, then you could actually make this magnetic by running electrical source through it. It becomes magnetic. Increase the current, becomes more magnetic. All right? Have a duplicate of this over on this side, and you can make a magnetic field just like bar magnets. But when you do it with solenoids, the benefit is the control that you get. Now that means that I could crank up the current, making these very magnetic, or I could reduce it, making them not very magnetic, and I could even switch them off, making them zero. So technically, I could have a loop that is static and just sitting inside, in between these two solenoids, and I could just switch them on and off. And without the loop actually turning or moving in any way, the magnetic field does all the moving. Okay? As the magnetic field goes on and off, on and off, and on and off, you get a magnetic flux change as it goes on and off, and you end up with current running through the loop that you're suspending in between these two solenoids. All right? So that's the third way that you can manipulate the situation. All right? Okay, so in this case, let's see. To investigate electromagnetic induction, the student uses the equipment shown below. It consists of a magnet which provides uniform magnetic field. So in this case, these are permanent magnets. They are connected to a CRO, cathode ray oscilloscope. All right. If you've never played with one, wait, here's one I prepared earlier. This is a CRO. Okay, so cathode ray oscilloscope. Cathode ray, okay. There's your screen, all right? Basically what it is it provides a picture of your voltage and how it changes, okay? So it'll give you, you can manipulate voltages in so many different ways and make the graphs look all funky and weird. You can make them, you could actually show an alternating current graph through here, you can show DC or whatever, all right? So when they're talking about a crow, they're talking about this machine, and it actually does not contribute in any way to the question itself, all right? So as far as you're concerned with the question, who cares what a crow is? Doesn't actually matter. They just want you to know that you're talking about the graph of voltage, that's all, okay? So this setup is being connected to a crow, so you can see what the graph is. That's it, okay? All right, so the student moves the coil vertically out of the field at a constant speed. Well, that's got a lot of self-control, like that, okay? The entire coil is within the field from 0 to 0.4 seconds, okay? So it's inside the field for that whole time, the whole loop, okay? It leaves the field between 0.4 and 0.6 seconds. The graph below shows how the magnetic flux through the coil varies with time. Now, from here to here, it's completely immersed. From here to here, it leaves the field. Okay, so it's gone from full flux to zero flux in that time. Okay, you can see here I've written a whole bunch of notes for you if you want to go back to this question. Which graph below is best to represent that situation? Clearly it's B, because you only have one pulse. You only have one movement where flux changes. It goes from full to zero. That gives us a negative gradient during which flux is actually changing. So that means there's only one motion that brings that can be responsible for giving us a pulse of current. So it can't be that. It can't be this or this or this either, simply because these imply you've got a voltage happening in here, even though for that whole time the entire loop is immersed inside the flux. So even if a loop is moving between two large magnets, right, the number of field lines entering that loop is the same as the number of field lines that are leaving it, okay? So while it's inside, say two really long magnets, okay, you're still getting zero, okay, even though it's moving, all right? Because there has to be a change in density inside the loop, not, it doesn't care if I added 10,000 lines when I lost 10,000 lines. It's like the density is the same, so you're not getting anything, even if it's just moving within the field, okay? So that's why it's only in the act of leaving do you actually get a pulse, and as I just described, that is it. And this value here would be whatever this gradient is. If this gradient was 5, rise over 5 over 0. Whatever that is, 0.2, okay, and it's 5 over 0.2, bam, that value there. That is what the pulse is. Down here, these are just dotted lines to show you that this is vertical. All right, these are nice horizontal. Okay, so that's why it's that. This would imply that it left the field and then re-entered it immediately. Okay, that's why it can't be that. All right. Shouldn't be too hard to get. Actually, this is what I'm showing you right now isn't the hardest part, okay? All right, okay, now here we go. Here we go. In this situation, we've got the diagram shows a flexible loop of wire between the poles and the electromagnet, which provides a uniform field B in the region of the loop, okay? At time equals 0, the current through the electromagnet is turned off. So right now, you've got a magnetic field, all right? You've got a magnetic field that drops to 0, okay? So, look at this curve as a series of changing gradients, all right? So how do you know which graph represents this, all right? Here, the gradient is negative and really high. It's very steep, okay? So if it's negative and very steep, you should have a positive EMF, okay? And it should be very high. This one or this one. These two are already out, okay? Now, does this gradient stay the same all the way down? No, it doesn't. If it doesn't stay the same all the way down, then it can't be this guy, all right? So right there you go, you have to say, oh, okay, it's got to be A, okay? Logically, it has to be A. But can you prove it, all right? So in this same time period, the gradient is really steep. Here it's about 1-ish, okay? So that might correspond to this value here right in the middle, okay? Because at least there seems to be some sort of symmetry here. And then here, the gradient gets really small and all the way to 0. Here, the gradient that you read off here plots points all along here. So as the gradient gets to 0, you can see, logically, it has to be A. None of these are even close to what's going on here. Okay? Again, have another read of it. It's a good question to link them together. All right, over here, we've got another one. Here's a nice little picture of a crow that I just showed you a real one. Student investigates electromagnetic induction using a single loop of wire and an electromagnet. As shown below, the loop is placed between the pole pieces of the electromagnet. Electromagnet meaning these are coils that create the electromagnet, and so in other words, you can control the field without moving the loop. And that's the point of this, okay? So that any induced voltage can be measured. The current in the electromagnetic coil is reduced so that the magnetic field B decreases to 0 at a constant rate over time. So, okay, so now the magnetic field is dropping at a constant rate, okay? So that gives us a drop that's constant, which gives us a pulse which is constant, okay? All right. Here I've actually created values to try and explain it again and just reinforce the idea that the gradient is measured off the y-axis of the EMF graph. All right. So what's the actual question? That'd help. All right. Which one of the figures A to E shown below best represents the variation of the induced voltage as a function of time? Well, again, all of these graphs are nice and straight, implying, oh, sorry, wait. In a second experiment, all right, so this is true, okay? So at this rate, you get this voltage in this time. In a second experiment, the magnetic field is set to an initial value that is twice that used before. So, what we're saying here is the field density is twice as strong, okay? And it's dropped in half the time, okay? How does that change what the pulse is, okay? So, I've gone through here and shown you that using Faraday's law, you can see that the voltage depends on how strong the field is, the cross-sectional area, and the time that you change that the field in, okay? So, as you can see, we aren't changing the cross-sectional area. It's the same loop, okay? But we have doubled the field. That doubles the field. So we double what's up here, okay? But we halve the time, okay, in which that it happens, in which the shutdown happens. So when you halve the time and you double the field, using your rules of fractions, dividing by t over 2 is the same as multiplying by 2 over t, the reciprocal, okay? So that's why you end up with 4BA over t. Okay, and that's where that comes from. And again, another example of why knowing fractions is really helpful. Okay, all right. So that explains why you can see here you have double the voltage. All right. So not double the voltage, 4 times the voltage in half the time. Okay, that's how that graph makes sense. All right. Now there's only a couple of other ideas I need you to really get your heads around. Aha! This here, seriously, is one of my favorites. Okay, now, this is about the direction of the induced current, and this is the last big thing you have to get in your head, all right? And often, out of the 3 chapters that we study for this outcome, for this area of study, this, I would say, is the bit that is the most difficult for students to get their heads around. But once you do, once it clicks, and you actually kind of pretty much own this area. It's really good, all right? Now, look at this situation carefully. We have a loop, got a couple of permanent magnets and a loop of wire that is going to be dragged in between the field, or in between magnets, so it's going to enter the field and then leave the field. So you can see here, it starts out here outside the field and it enters the field here, where there's a nice, because it's a nice square loop, we've got a nice predictable, nice linear increase in flux, which gives us a pulse of EMF. Now you can see, which way should the EMF go? Well, that's a positive gradient, so the EMF should be pulsing negative, okay? And it should be constant because this is a constant gradient, okay? So you should be able to see that now. It enters the field completely. While it's in here, as I described earlier, the number of field lines entering the loop is going to be the same as the number of field lines leaving the loop, because you're imagining the density is quite uniform across between the poles, which means we have constant flux through here. And if you have constant flux, what EMF do you have? Did everyone yell out 0? Yes, that's right, you have 0 because there's no change, all right? Then it hits the outside edge of the field and empties of flux. That's the reduction. And then once it's out, 0 again, okay? So 0 EMF, 0 EMF, 0 EMF, pulse, pulse. One down, one up. Easy, totally get that, all right? And here you go, like the graph there tells you that. Coming in, pulse up, inside, pulse down to leave, then nothing, okay? But that's not the most interesting part of the question, okay? The more interesting part of the question here, and this is obviously part of a much bigger question from an exam, and a question that gets asked often, actually, in exams and SATs, is which way does the current run through the microammeter? Okay, does it go from the left to the right, or does it go from the right to the left? And using Lenz's law, you can actually figure that out. And yes, it is as exciting as I'm making up, all right? So, let's imagine what's going to happen here, okay? This loop is about to enter the field. Now, this is a face-on view of what's going on. So we're facing the North Pole. This is important because you have to orientate yourself. So I'm going to face the North Pole straight in like this. And I'm going to say, okay, what is going to happen to the flux in that loop, all right, as it enters, okay? As it enters, I'm going to first focus on the leading edge, because if I focus on one spot, it tells me what's going on everywhere. So as I focus on that leading edge of that loop, as it enters the field and then leaves it again, I'm looking at this front edge of the loop as it hits the field, okay? And then enters, all right? Now, this is how Lenz's law works. If a loop fills with a field, okay, that's moving out of the page, Lenz's law says that a current will be induced in this loop to oppose the change that made it, okay? Now that doesn't make perfect sense yet, but it will. As the loop hits the field, it is going to fill with these magnetic field lines from the magnet coming right at you. Now we know it's cutting these magnetic field lines, which means a current's going to be induced in that loop. And that current is going to create its own magnetic field. And that own magnetic field needs to oppose what just happened. So what is the opposite of filling with a field coming right at you? Well, the opposite is filling with a field going the other way, okay? So I grab that red side, and because basically my fingers have to go inside the loop, all right? They must be inside the loop, and they must oppose what is happening. So all of a sudden you've got nothing in there, right? You enter, all of a sudden it's full of magnetic field lines. Well, how do I get rid of them? Well, I'll try and cancel them out. If I put two fields up against each other, then the vector sum is 0. I can pretend that I don't have any field in here, right? So what I'll do is I'll go bam, fingers straight through the loop, okay, to oppose this change, okay? Which way is my thumb pointing? What does that mean? Well, to make a field going down, I must have induced a current going this way through the loop. All right? So in other words, if that is the direction, then as this loop enters, the current runs from left to right through the ammeter because it had to. It was as it entered, it was down, moving this way, going up this arm and through the left side of the ammeter. Okay? That's Lenz's law in action right there. All right? Lenz's law just tells you, how do I oppose the change? Now, you look at that, you let it sink in, and you're like, yeah, this isn't too bad. Is this the hardest thing, really? Actually, it only becomes difficult when you try and consolidate what happens when the loop leaves the field. You have to really get the idea of what does opposite actually mean, all right? So, let's finish this off. If you fill with a field, now the operative word here is you fill with a field that is coming out, you will oppose it by filling with a field that goes out. That's opposite in this context, all right? When the loop now reaches the outer edge, here, okay, it starts to empty. So once it enters, it'll try and fill with a field that goes in. Once it actually crosses inside, then that's it. Nothing else happens. That's gone. The current stops. That field that was associated with it is gone. The field that's pointing into the page is gone, while it's sitting in there traveling along happily. Then it hits the outside edge. Now, when it hits the outside edge, it tries to, well, what's going to happen is, exaggerated here a bit, is it's going to go from having a field lines that are doing this, coming at you, to nothing, all right? So what's the opposite of emptying of a field that's moving out? The opposite is filling with a field that is moving out. So the opposite in this situation is when it leaves, the opposite of losing your field coming out is putting it back. That's what is actually going to happen, all right? Now, as it empties, you wrap your fingers in, because now it's in that empty region, to try and put those dots back. So while you exit the field, that is happening. They're putting them back. Which way is your thumb pointing? Straight. Now I'm focusing on the outer edge. My thumb is pointing up. Okay, so which way is the current moving? It's moving up through this arm. Okay? If you look back here at the loop, through the ammeter, micro ammeter, it's now moving this way, right to left. All right? That, believe it or not, is the hardest thing kids find in this bit. All right? What does the opposite of what's going on actually mean? All right? If you are filling with a field moving out, you want to cancel it out. So you go field moving in. If you empty of a field coming out, then you want to put it back. So that is the whole idea of where the pulse goes up on the way in. So that is one direction of the induced EMF. And when you exit, it's flipped around. The pulse goes the other way, okay? That is the whole idea of Lenz's law and how it applies to Faraday's law of induction, all right? Okay, now I've done heaps of these questions, not every question because some of them are just obvious repeats, okay? Here, I want to just have a quick chat about this one. We're nearly done. I know this has gone on forever, but wait till I try. You should be there when I'm trying to edit and cut it together and export it and package it and That takes hours. Here, this wire gets pulled out, all right? This wire gets pulled out of the field, all right? Now, these wires are running, these side wires. You can see that if this was like a bed of nails, right? That those side wires, to pull them out this way, wouldn't hit any nails, right? So these wires are not responsible, these wires here are not responsible for the induction of any voltage or any current, okay? They're not responsible. The only wire that is responsible is this one here. Why? Because you can clearly see that it's slicing through magnetic field lines as you pull it out. So a couple of things happen here, all right? A couple of things happen here. As you pull it out, you're going to get an induced current, all right? Which way will the current go? Okay, and here's another little opportunity to practice the idea of which way things are moving, all right? So, which way will the current run through this loop if this switch was closed? Okay, so if that switch was closed, which way would the current run? Okay, so this is a job for the right-hand rule. The right-hand rule says that I will induce a field, a current, that will in turn induce a magnetic field that will attempt to oppose the change, okay? So as this loop moves out, okay, what you can see is, by the right-hand rule, you can say to yourself, well, if I'm pulling it this way, it's going to try and resist that pull. Okay? So, it's going to experience a force out. Okay? So if I line my hand up now in the same plane as that wire, okay, with the field lines north to south acting down, my palm trying to oppose the pull out, okay, my thumb points this way down the red line. So that tells me straight out, the current must run this way. Okay? So that was my right-hand rule, just using the idea that the forces need to oppose, just like the magnet falling through that tube. All right? That's one thing that's important there. Okay. So which of the, now that's just something I wanted you to sort of get your idea around there. Okay. Now it is a square or rectangular loop. It is exiting the field uniformly. So you're not expecting a curvy line or anything like that. It goes to pains to tell you that the switch is open. And this is to get students to go, oh, with the switch open, nothing's going to run no matter what we do. So it's going to be A, right? As the loop is being dragged out, even though the switch is open, it doesn't actually stop the fact that electrons will still build up in the conductor, okay? They'll still build up at a particular end, all right? So in response to those field lines cutting the conductor, there won't be a flow of current, but there is a voltage, which means as this uniformly empties, the actual answer is F, okay? It gives you one nice pulse, okay, of current as you leave, all right? So basically, even though the switch is open, you will still have a build-up of charge in the length PQ as it cuts the field lines. Now, this is very similar to how when you reverse bias a diode, okay? If you reverse bias a diode, you get zero current flowing in the circuit, okay? But you get the total voltage drop, all right? So if you imagine the open switch as infinite resistance, that's the way I thought of it. It does not mean that there's no voltage, but it does mean there's no current, okay? And why it made it that answer, okay? All right, so I wanted to get to that question because that was kind of important. Now, last couple, all right? Last couple, which basically, now I did up to about 40 of the questions. And again, just ask if you struggle with any of them. But here, I just want to cover some of the classic examples that you see over and over again in Saxon exams for this kind of thing. So, which movement of the magnet or magnets will produce the greatest deflection in the galvanometer? So what's a galvanometer? Galvanometer is just a fancy word for another ammeter, okay? So it's an ammeter. You just take it as an ammeter, all right? Now, you can see here, I've got D as the answer. Why D? In this situation, it doesn't matter if your magnets are entering the field, the coil, or exiting the coil, okay? They both of those versions induce current, okay? In this case, you've got a north-south, south-north. You've got basically a very, you've got a magnet here that has field lines moving in all sorts of directions that sort of cancel each other out, okay? So this is not helpful, okay? Over here, you've got a magnet exiting the field at velocity v. They look exactly the same, except that this one is at twice velocity v. All right, so this is moving much quicker. And as you know, Faraday's law, the faster you move, the more current you get. Okay, the more voltage you induce. C has fewer coils. Fewer coils means less induced voltage. The more coils, the more you get. Okay, so that's why it is D. Okay, now let me ask you, which way, if we look at option D, which way will the current that is induced in this coil run through the galvanometer as this north pole, as this magnet leaves the coil, okay? Which way will current run through here? You can actually determine it, and you need to know how, all right? Again, it's not asked in this question, really should be though. Okay, look at what's going on in this situation. This is another example of the field exiting, of a loop of a coil emptying a field, okay? So if it's emptying, okay, now you can see through here, this is the magnetic field emanating from the magnet, north to south, okay? So this solenoid, while the magnet is close to the solenoid, it is full of a field that is moving to the left. It is full of a field moving to the left. When the magnet is taken away, it is emptying of a field moving to the left. What should happen by Lenz's law? If you are emptying of a field that is moving to the left, you have to put it back, okay? So, to put it back, you need to grab the outside rim of the outer coil, grab that coil, and thread the coil with your fingers moving in the direction that signify what you're trying to do. You're trying to put that field moving to the left back in there, all right? Because it wants to maintain that, all right? So, that means your field moves through the coil this way, okay? Now your thumb, if you're imagining your hand wrapped around the outside of that loop, your thumb is pointing up, okay? Which means all of the coils have the current moving up. Now, let's put this right hand grip rule away and take out the north finding rule. Here it is. Take out the north finding. Put your fingers in the direction the current is moving. Okay, that tells me that the solenoid, as this magnet leaves, forms a north pole on this end and a south pole on this end. Does that make sense? Well, actually it does. If the solenoid is attempting to stop what's going on, okay, then it makes sense that a south pole will form here because because a south pole will be attractive to a north pole. It will actually inhibit the pull. Like, so someone's got their hand pulling this magnet away. You should feel a pull back. That's Lenz's law in action, okay? Again, the magnet falling through the tube. It opposes what's going on. So if I'm moving a north pole away from a solenoid, a south pole will form here, okay? For a south pole to form there, it means the current through the solenoid should be going in that direction, because there's my south pole, there's my north pole. Which means if I follow those lines along, that's that fine line that goes around the back, comes out through the back, it goes through here. So through the galvanometer, the current moves in that direction. Now, what if I push the magnet back again? What happens then? I mean, logically, that should reverse everything. Does it? Okay, let's see. Let's rub all this out. And what we're going to do is we're going to try and push the magnet back in again and see if it changes the direction of the current through the galvanometer, which it should, of course. So now what we're going to do is we're going to imagine this arrow is going the other way because we're pushing it back in. We've got this field. Now, to push the magnet back into the coil, we're going to have to imagine that the coil was empty of magnetic field lines. So, if the coil is empty of magnetic field lines, and all of a sudden it finds itself filling with a magnetic field that is moving to the left, what is the opposite of that? Well, it wants to remain at zero, where it was happy, okay? So it wants to cancel out what's going on. Hence, thus, therefore, it's going to fill with a field that opposes this motion. In other words, you have to try and thread your fingers through the solenoid in the other direction. As this goes in, it's like, no, I don't want that in there. So, bang, does that, okay? So the field has to move in the opposite direction. So the field that's induced goes that way, okay, as per Lenz's law. Now, if it's moving in this direction, that means a north pole forms here and a south pole forms here. For that to happen, my fingers need to be wrapping around the coil like that, so my thumb goes this way, so that's my north binding rule. That tells me my current's running down. And if my current's running down, notice it comes down that way. Oh, there you go. Through the galvanometer in the opposite direction. Now, does this make sense is this consistent with Lenz's law? Well, Lenz's law says that there'll be forces associated with this that oppose the change. So if I try to push a north end into a solenoid that's initially empty of field, it's going to try and resist that. Well, how would that practically appear? How would that practically work? Well, if a north end forms at the entrance during that motion, those two norths will push on each other. That is the opposition that it feels, okay? So it does make sense in every context, every version of how you look at that situation. Again, super important to understand this idea. Otherwise, if you don't understand this idea, it makes the whole thing really, really hard to do, okay? And again, there are 80 questions here, plus your checkpoints, okay? So by the time you finish listening to me, you need to attack a bunch of questions all by yourself and do everything you can to try and make what I'm telling you make sense in the context of those other questions. And you check the back of the book and you go, oh, I got it wrong. And you figure out why you got it wrong. Okay, then you do another one, you get it wrong again. And then you do another one, you get it wrong again. And that's fine, it's fine. You know why? Because the 5th one down or the 10th one down or whatever, you're going to get it right, and it's going to start to make sense, because learning is not just like a light switch, all right? It takes time to figure this out. It took me time to figure this out, to really get a handle on what was going on. I had lots of people tell me how it worked. Didn't help, all right? Really didn't help. In the end, it was just me. I had to go, oh, okay, I get it now. This is what's going on, all right? And yeah, so it's really important that you put that time in. Okay. This question has the loop rotating that way. Read the question. I don't need to go through this. It's just going to extend your video even longer. There's a lot of notes there. Basically, the idea is that it's this graph here. As the coil rotates, it empties of the field. All right, so it's a negative pulse. So it's a negative gradient of flux, which means it gives you a positive pulse. Okay, and it's gradual when it starts at the vertical and starts to move. The pulse is gradual. And then when it gets to that point where it goes from some area to 0, that's when you get your sharpest pulse. And that's why you've got that sharpness there, where it then drops and then starts again the other way. All right? Okay, that I don't want to spend too much time on all of that. Let's see. Again, just interpreting the graph. It's a bunch of words there. All right, what about this one? This one, again, in detail goes through what I just went through with that other example where it didn't actually ask for that question. But in this question, it does ask for, well, which way is the current actually going to be running? All right? So read through that. Be very careful. I've drawn lots of diagrams there. Again, you know what? Again, lots of detail here. You don't need me to read it out to you. They've actually put in this one here, in example 17, their own answer. Here, I reckon mine's way better than theirs. Over here, this is another question, all right? Often you'll find what they'll do is they'll give you 2 coils. One of them will have a power supply attached to it, and the other one will just have like an ammeter or something in it. Okay, and so this is another really good question that you probably want to see if you can answer yourself. All right. Now, if you can't, I've gone through. You start here. You read this. You read this. It takes you through every part of the question so that you can it gives you a logical starting point and a logical conclusion on why it is the answer that it is. All right. Again, you need to do the basic things where, look, there's a battery there, right? So I put a plus on it. I put some arrows on it. I knew which way the current was. These are the basic things you must do, all right, when you're trying to do a question. Okay. There's no point going, I don't get it, and I didn't know what to do. It's like, no, it's do the basics, okay? Every little bit builds on the next little bit. So when I put my plus there, that tells me there's an arrow that goes this way. That tells me that the coil runs this way. That tells me that the north end is here and the south end is there, okay? And if a south end forms here, that tells me that there's a field washing over this coil that is moving down. So what's it going to do? Well, it's going to try and oppose that. So it's going to create a field going the other way, okay? As you fill with a field going one way, the natural opposite is to try and fill with a field going the other way to cancel it out. Bam, okay, the field's going that way. That means there's a north end there and a south end there. Oh, what does that mean? Well, that means if that's true, that's the north end that way. That means the current's running this way, all right? So all of it is logical. All of it makes sense, but it's not like you can just stare at it and go, oh, that's the answer. You've got to build up to it. It starts there with that little plus. There, that's where it starts, all right? It finishes with the answer, okay? But there's nothing's going to happen if you don't at least put down the first thing, okay? All right, let's see if there's anything else here that is interesting. No, these are all just rehashes of the same thing. Again, pushing a rod through wire, through a field here, a magnet moving through a copper tube. Okay, again, lots and lots of notes for you guys to attempt to go through and attempt. Okay. There is one thing that I haven't actually covered yet, and this is the last little bit. Generators and alternators, all right? Here, you have one of these as a diagram, okay? So, what you're looking at here is a generator, okay? Now, there's a little green light going again. All right, that generator. this is a generator and gives you this signal right here if you are connected to slip rings. In other words, a constant unchanging connection. All right? Unchanging connection gives you an alternating current. That is, it's where it gets its name from, the alternator. All right? Which is another word for generator. Okay? So it's an AC generator. All right? Now, that is if you're connected, if one of these arms is connected permanently to one ring and the other arm is connected permanently to the other ring. Remember, that a slip ring is basically a ring and that there is a connection that touches the inside of the ring and it moves around. So it can maintain a connection without twisting, okay? So that's how you can connect a spinning object to another object while maintaining an electrical connection, all right? Now, so one of those arms is longer than the other and that's how that works. So as it spins, you get an alternating current, okay? Now, let's say you take your generator and you attach a split ring commutator to it. So there's my little split ring commutator. There's the split through there, so there's a gap. So for half of the turn, one terminal is connected to the pole, connected to one side of the loop, and for the other half, then the other one is. So it kind of does the exact same thing as in an electric motor. In an electric motor, it takes a direct current and it flips it around every half turn through the loop so to maintain your torque in the same direction. Remember, we did all of that. In a generator though, rather than producing an alternating signal, by using a commutator, you actually end up with what's known as lumpy DC. It takes all of these bottoms and flips them up because the commutator reverses the current every half turn. So it ditches the bottom halves and does this, okay? Now you can imagine if you had multiple splits, okay, and multiple loops, that you could actually really smooth out that curve, all right? You could smooth it out to the point where the average power output is actually quite flat, okay? So using an AC, basically an alternator, to create a DC output like a battery, okay? So, don't forget that. That is an important little idea. Slip rings, AC current. Put a commutator in there, lumpy DC, right there, all right? That is something that you need to remember, okay? And, oh yeah, as you take a loop and spin it in a field and speed it up, two things happen. The output, the amplitude, so the voltage goes up higher and higher, but because you're spinning faster and faster, the period gets shorter and shorter. So as you speed up, that is the period of the first cycle, one rotation. There's the period of the next cycle, so it's getting faster, so it's taking less time to spin around, and that is why this is the correct answer. There's a full cycle, full cycle, full cycle, and so on. All right? All right. Please don't forget that frequency, that's not it. Okay. Frequency F is in unit hertz, okay? And sometimes I'll say, oh, it's spinning 10 times a second. 10 times a second means 10 hertz. Okay, that means F is 10 hertz, all right? But you need the period. How long does it actually take to turn around one time? Well, the period is equal to 1 over the frequency. And obviously, the frequency is equal to 1 over the period. So, whichever one you need, all right? So 1 over the frequency in this case would be 0.1. So that is your period. In other words, seconds. So if a loop is spinning at 10 hertz, the period of one turn is 0.1 second, okay? Which means that half a cycle is 0.05 of a second, and a quarter, so motion up to then down, a quarter is 0.025 of a second. They're all very important values to consider when you're doing this work. Was there anything? Here's another nice, a much more blown up version of what the split ring commutator looks like and what a slip ring looks like. Okay? All right, but an easy question, so I haven't really done it. Again, same idea, that's what I just covered then. Over here, yeah, that's a good question. Have a look at that, that's good. There's, yeah, another good one. Anything else, anything else? Yeah, okay, here you get the idea of the relationship between frequency and period. It's detailed beautifully in the question. Like there's no substitute for just getting through them, okay? All right, so have fun with that. Don't forget to ask anything, anytime. I'm always available for help, all right? If you don't have, in this sort of self-isolation thing, if you don't have a proper study routine, you really need to make one. One thing I learned early on was you don't wait until you're in the mood to do your work, because it's work and work sucks, right? That's why they call it work. If it was fun, we would just call it fun, right? So don't wait to feel like doing your work, because trust me, that feeling's never occurred to me. I've never felt like doing my work. I've just had to, all right? So you set times for it if you need to, okay? Don't go one day, another day, and another day of, oh, I'm still waiting to feel like doing my work, all right? That's just nonsense. You just set a time, you set a program, and you do it, all right? I'm not saying every day has to be exactly the same. I'm just saying that you plan out a week so that everything gets covered, all right? And that way you don't end up in a sack with a help sheet that's got nothing on it because you didn't do any questions, and then feel bad about it later, all right? So you need to actually focus and do it, all right? It's year 12. It's effectively 8 months of your life, all right? That's it, okay? It's nearly over now, all right? Okay, we will catch up soon, I hope.